How are y'all today? Good. Does anyone have any objections to having the lights off? All right, if it's an issue, just let me know, I'll turn them on. Does anyone have any questions on the homework? We've got our first exam a week from today. So there's one more thing in 2.6 we're going to talk about, and I realize this might not be in your notes, so I'm going to go ahead and pass this out. If you want to reference this. Just trying to save paper so they're a little bit smaller than a full page. You're welcome.
Oh, that's just for I thought we had to pass it down.
Okay, this theorem we're going to look at deals with continuity, and you'll notice a lot of theorems that we discuss will bring up the word continuity. So this intermediate value theorem says that if you have a continuous function on an interval, a and ab, closed interval ab, and L is some y value strictly between f of a and f of b. So the y values that correspond to the endpoints, f of a and f of b, L is some y value in between those two. Then what that means is there has to exist a c, or an x value they're calling c, in between the a and the b. So this is, the two figures on the right are just an example of a situation that the theorem's talking about explicitly. The first one, we have one possible c that equals this y value of L, but we could also have multiple c's, c1, c2, and c3. So the theorem, it's stipulated there exists at least one if you've got a continuous function, and these two conditions, f of L is in between f of a and f of b, is satisfied. The figure on the far right is illustrating that if the condition or the hypothesis or the assumption of the theorem is not true, then you can't guarantee that there's at least one of those L's. So this is just one example. We've got a function that's not continuous between a and b, and if we wanted to know, like if we had this particular y value here, because you can see there's no input on the x-axis that would actually give us that y value. Okay. So this theorem is often used to determine if there are solutions to a particular equation. So a lot of times you have an equation and it says solve this equation, and you spend a little bit of time or a lot of time solving the equation just to come out and say, well, this doesn't have a solution. So a lot of times this theorem is used to determine if there is at least one solution before you go off and try to find a solution, because it's, as you'll see, it's a pretty simple thing to check in practice. And we have all of our rules for continuity, all those theorems for continuity that we can use to justify whether a function is continuous or not. So typically, you'll see this in application 2. Hey, here's a function. Does this function ever equal to 5 on this particular interval, or is this function ever 0 on this particular interval? And that's kind of how we'll see it. But also, like when the computer or your graphing calculator graphs a function you input, it's kind of using this notion. So the intermediate values are just all of these values in between this point and this point. So we can consider all of these things intermediate values. And when your calculator or whatever plots a graph, it doesn't physically plot all of those points, right? There's no way it can. It just plots a couple of points, in some interval, like if you told it to graph x squared, it's probably going to do this. The calculator or the computer assumes the function you're dealing with is continuous because it really doesn't have a way to check if it's continuous or not. It just assumes the function you're graphing is continuous, and then it sort of just fills in all of these intermediate values to give you the graph. That's why a lot of times if you've used Desmos or other graphing software, you'll see a curve like this, and you'll say, oh yeah, it's totally defined everywhere. But when you put your mouse on this point right here, it might say, oh, this point is one undefined. But it's only when you click on this thing specifically that it tells you that's undefined. If we're just looking at it from afar, it looks like it's all connected. Again, because it's just plotting a couple of points and then filling in the intermediate values. Okay. So like I said, the way we're going to use this theorem is just to test for specific solutions. We're going to be given a function, and we want to know, does that function ever equal a certain number on a particular interval? So an example of that, I don't know. Just curious, did y'all have that in your notes if you printed out these notes? Okay, some like my notes didn't, they weren't there, but if you printed them out, I guess they were there. But anyways, the example says use the intermediate value theorem. I'll just abbreviate that. Use the intermediate value theorem to show there is a solution. To the equation 4x cubed minus 6x squared plus 3x minus 2 equals 0 on the interval or between the closed interval from 1 to 2. So you'll see, this is using this theorem, it's a pretty quick check to determine there is a solution. The theorem, intermediate value theorem, will never tell you what the solution is. It'll just tell you if there is one. So the theorem doesn't find what this C value is. We just know there is one, at least one. Okay. So even a cubic equation, they start to get a little bit difficult to solve, right? You've got to really, our strategies are to find the rational zeros, possible rational zeros, and then you do synthetic division in hopes that you find something that divides into that, right? This is a lengthy process. So, even before you try to solve that equation, you might use something like this to say, well, is there even a solution before I try to find a solution? Okay. So what we're dealing with is, with respect to the theorem, we can view this right here as our function. We can view 0 as the number L. And then our interval here, of course, this is our A and our B. Now, there's many ways to rewrite this equation. So there's many ways to say, use the intermediate value to show that there is a solution, blah, blah, blah. So, this thing could have been presented to you as use the intermediate value theorem to show that there is a solution to this equation. If that's the case, if you're presented with, this sort of the second variation, then what you want to do is take all of the variables, all the x's here in this case, and put them on one side. That number L that shows up in the theorem is a number. It's not a function of x. Okay. So if this were the case, we could say, well, let me find my function of x. It's 4x cubed minus 6x squared plus 3x. And then I could say, does that ever equal 2? And I could answer that question exactly the same way we're going to answer the original question, right? Because it's the same statement. But the important thing is that on one side you do have a function of x, and on another side you have some number that's going to be your L in that case. Does that make sense? So never use this theorem to set two functions equal together, or to equal to one another. All right, I'll sort of put this aside. The alternative version. So what we want to answer is, does our function above equal 0 when x is in between 1 and 2? Okay, so the first thing the theorem says is, before we apply any of the stuff that follows, is suppose f is continuous on the given interval. So if you're going to use the intermediate value theorem, the first thing you need to do is establish continuity on the given interval. So first, you always have to answer, is the function is that function continuous on the given interval from 1 to 2? If you don't somehow justify that and use the theorem, then it's not fully correct. So we have all of those theorems. You don't have to remember verbatim what all of those theorems said, just like in gist what they tell us. Well, we had a theorem that said polynomial functions are continuous on their domains, all real numbers, right? I don't remember what theorem that was. I don't remember exactly what it says, but I do remember that we had a theorem that told us polynomial functions are continuous everywhere. So that's all I need to reference. F of x is a polynomial function. According to theorem, whatever it was, they're continuous on all real numbers. That's all we're going to say here. You just want to, even if it's a simple statement and it seems very trivial, like why would I even list that if I already know that? The reason you're stating that is to show that you know what the conditions of the theorem are. So we're going to say, yeah, f of x is continuous. So we're going to say, f of x is a polynomial. And thus, it is continuous for all real numbers, which certainly then means that it's continuous on this little interval we're given. All right, so we've got sort of the hypothesis of the theorem out of the way. Then we can go on to the next statement of the theorem. So the theorem says that if L is a number between f of A and f of B, so we're asking, when I compute my function evaluated at 1 and then my function evaluated at 2, is my L, in this case it's 2, is 2 in between those y values that I get? So that's the second thing. You compute. These are always the steps when you utilize the theorem. So the second thing is just to compute f evaluated at the endpoints and see if your L is in between those two values. So again, we're going up to the theorem just to point this out. It says if f is continuous on this interval, And we have this L between f of A and f of B. Right, so that's the next thing we have to check for. So we're computing f of A, which is 1, and f of B, which is 2. These are, I'm just going to write down the function again. Oh, sorry, our L was 0. That was minus 2. That was our function. So we'll just, but we wanted to know, that was our rearrangement when L was 2. You could see that once we've computed f of A and f of B, we could compare that sort of second version of our question. But the L we're looking at is 0, and of course that changes the function, right? If you're saying, okay, well, when is this thing equal to 2, then you've got a slightly different function than the people that are looking for 0 do, right? So just keep that in mind. So, but this is our function. Now we're going to evaluate our function at the endpoints. So we're going to evaluate f of 1, and we're going to evaluate f of 2. Our endpoints to see what we get. So, you know, that's just plug that into your calculator. F of 1, it gives us -1. Oh, we did this here. F of 1 is -1, and f of 2 is 12. So there's our function evaluated our endpoints. We've got one y value of -1 and one y value of 12. And we know the function is continuous in that interval from 1 to 2. So, you know, we could write out the conclusion right now, but visually, let's just see what that tells us. I'm on this interval from 1 to 2. I have no clue what my function looks like, right? We didn't graph that function at all. But we do know that f of 1 is down here at -1. So the function has a point right there. And we know that f of 2 gave us 12, you know, somewhere up here. Not to scale, but. So we know our function definitely has those 2 points. But more importantly, we know that in between here and here, the function is continuous, right? Which means we can connect these 2 points without ever having to pick up our pen. Yeah? So since the function is continuous, I have no idea what it's doing. It could be doing something, it's not doing something weird like that, but it could be. I don't really know any of that. All I know it's continuous, so all of that's connected from endpoint to endpoint, right? And so the L we were looking for was 0. So yeah, that means somewhere this function has to pass through 0. If it goes from -1 to +12 and it's continuous, it has to pass through 0 to satisfy those conditions. In other words, we know from -1 to 12, since this function is continuous, that it takes on all intermediate values in between those 2 points. Specifically, we were looking for when it's equal to 0 right here. Okay, so that's our conclusion. We would say something to the effect of, you know, this tells us, and the fact since f of x is continuous, since f of x is continuous, and our L, which was 0, is between -1 and 12. What's our conclusion? What's the conclusion of the theorem? There is a solution, right? So you can say there is a solution. Specifically, they're saying that if, you know, I guess y'all can refer to in the handout, but it says that if these two conditions are satisfied, as in this case, there exists at least one C. So there exists at least one solution. That's the best we can determine. We know that it passes through 0 at least once, but we also know polynomials do weird things, right? We also know that polynomials could come through here, cross through here, and then end back up here. So there definitely could be two x values for when the function's 0 in between 1 and 2. But again, the theorem just guarantees that there's at least one. So that's the best we can say. Since there's the law between -1 and 2, there exists at least one. No, that wasn't good. Let me move that down so we can keep our conclusion together. And if you get confused as to, like what your conclusion should be, you just draw out a little picture of okay, well, I verified it was continuous, and I verified these two y values are on that function. There exists at least one. C in the interval from 1 to 2, such that f of that c value is equal to our L, which was 0. If you want to say that, since I verified both of those conditions in the first step and the second step, if you want to say that means there's at least one solution in the interval, that's fine too, because it's the same idea. Does anyone have any questions on this? Yeah.
By knowing the endpoints, how can we officially say that there is at least one value of 0? How does that help us at least come to that conclusion?
So by knowing the endpoints, how can we say there's at least one solution?
Just because it crosses over the axis?
Well, you're right. But how do we know that it crosses over that axis? Because the function's continuous, right? If this function might not be continuous, so it might do something like this, and then pick back up here like this, and then continue here. In which case, if it wasn't continuous, you could have this situation occurring. At which point we would say, well, just because I know this endpoint's here and this endpoint's here, doesn't mean that this function is going to cross 0. It's only because we have the endpoints, and more importantly, we know it's continuous.
But if both of our endpoints happen to be on the same part of the negative or positive y, we'd have to know more.
Yeah. So like if we're trying to say, well, where does that function ever equal 0 in this interval? And we came up with an endpoint at -1 and another endpoint at -2, let's say. All we know is it's continuous from here to here, right? But another situation could possibly be that from here to here the function does do this. So yeah, so what you're asking is what happens when the conditions of the intermediate value theorem are not satisfied, and we'll write that down. But if neither one of these conditions are satisfied that we did in the first and the second step, then all you can ever say with this theorem is that it's inconclusive. There could be a solution, there might not be a solution. It's inconclusive. Okay, so let's go ahead and write that down. So we'll say if either f of x is not continuous, the interval AB. Well, it's the closed interval, sorry. If the function is not continuous on the closed interval, or L is not between f of A and f of B, we'll just say the intermediate value theorem is inconclusive. So just make sure we know what we're saying when we say something's inconclusive. Doesn't mean it's true. It also doesn't mean it's false. So let's take a look at our function. All right, so there's our function, and we'll kind of zoom in so we can see the interval from 1 to 2. Now we can see, visually, it's super easy to verify, right? But we knew the function was continuous, and we computed two y values of the function to get the same information without having to factor it and graph it and do all of that. Okay, so there's our solution, is actually at 1.22. So if we did find the solution, that c would equal to 1.221. But the theorem doesn't tell us where it's at. The other option is that, okay, now that we know, and you could utilize this way. I believe computers or some algorithms will find zeros this way. It'll say, all right, well, I know that I have a 0 in between 1 and 2. Let me shrink that interval. Let me look at the interval from 1 to 1.5. Is there a solution in that interval? Yeah. All right, well, I'll shrink the interval, and I'll go from 1.25 to 1.4. Is there a solution in that interval? Yeah. Make the interval smaller and smaller and smaller, and eventually you can hone in on that particular solution. But for us, that's kind of tedious to make all of those computations. For a computer, it could do it, in half a second to determine where that zero's at. But that's what we utilize it for, just to know if there is a solution or not. I'm going to put this graph in our with our work. I guess I need to. I don't know if we have room. Oh, yeah, I'll just put it here. All right, do y'all have any questions on that? I did look through your textbook, and I didn't come across an example where the intermediate value theorem was inconclusive, so I don't have an example for that. I could probably find one. It's just something that I thought of last minute, and I don't believe you should have any examples that are inconclusive, but you should know that it's inconclusive if either one of those conditions are met. But, all right, I think that's the end of 2.6. Are there any questions on 2.6? All right, then we'll move on to 2.7. The before we, I'm gonna just add a page before. Before we actually talk about the actual definition of a limit, we're gonna look at a concept. So remember the limit stuff that we've looked at so far. It said, you know, for x that's sufficiently close to a, for all for L that's arbitrarily close to y, or whatever. You know, those words were just sufficiently close or arbitrarily close. The definition that we see here in 2.7 does actually make that precise. Like, what does it mean to be sufficiently close to something? But we're gonna sort of revisit absolute value stuff. Particularly things like this. Particularly that absolute value statement. We'll just kind of motivate that with an example. If you're thinking about the absolute value of something, let's say it's less than 3. Does anything visual come to mind when you see something like that? Yeah.
I mean, it's where one's going to be like, so the 3 is going to be greater than the x, and then the other one's going to be less than x.
Right, yeah. So we have, so like, if we're gonna visualize that, we would say, all right, well, I know my x is less than 3. So we'll just say it's 3 here. But I also know that it's, or sorry, I know the absolute value of x is less than 3, but it's also larger than, or larger than negative 3, I guess we would say. So, I don't know, maybe when you first saw absolute value, they said, when you see absolute value of x, just think of it as the distance from the origin. Do y'all remember that, hearing that? So, right, any one of these numbers I pick will satisfy that inequality. If I chose negative 2, the absolute value of negative 2 is 2, that's certainly less than 3. The absolute value of 2.9, certainly less than 3. So any of these numbers in that interval would satisfy that inequality. It's a distance from the origin to 3, not including 3, of course. So, you know, a less common way to write that is x minus 0 is less than 3. You know, you typically don't see it that way, but we want to start thinking of this particular absolute value statement in a specific way. So when we look at the definition of the limit, it actually has a chance to make sense. Okay, so the way we're reading this statement, we'll say is the distance from 0, and then since we have an x, it's clearly indicating the x-axis, the distance from 0 on the x-axis is no more than 3 units. So, you know, that's one way to think about it. I guess we could also like restate that sentence, but when we see an absolute value inequality like this, we want to think of it in those terms. Like a distance from something is less than something else. Okay. Or, you know, let's write this out. On the x-axis, we are less than three units away from 0. So it's kind of the same statement. Just depends on how you want to think about it. What if maybe we'll look at one or two more, hopefully just get the idea pretty quickly. But what if I wrote the absolute value of x minus 4 is less than 6? I guess the other way to look at this, after we look at this example, we'll write down what this statement actually means. In other words, how do you get rid of the absolute value? But we've already described in words how to get rid of the absolute value. So keeping this same notion of words that we had above for the absolute value of x minus 0 less than 3, what would we say here? What does this entire statement mean?
Less than 6 away from 4.
Right. So we would say we're dealing with x, so we're going to think about on the x-axis, we are less than let me write these in different colors here just so 6 and 4. So on the x-axis we are less than 6 units from 4. So visually, that means we're less than 6 units. We can go all the way out to 6 units from 4 to the right, which would put us right up against 10. Or we could go 6 units to the left, which would put us right up against -2. I think it's important to interpret the absolute value statement in these words. So like I said, when we see the definition of the limit, you've got 2 of these kinds of statements in there. So this is a more general statement, and we'll look at mathematically how we get rid of this. So we have the absolute value of x minus a is less than something. We'll just call it n, or some number. Is the same thing as saying that x minus a is less than the number. X minus a is also greater than the negative of that number. So this is the same statement as this. And of course, this statement here, if we add a to both sides, means x is less than a plus n, and x is larger than a minus n. So like there's the picture we were looking at, right? Here's some x value, x is here, whatever. It gives us a window in this direction and a window in this direction, right? This direction and this direction. So when we see this statement, the absolute value of x minus a is less than n, what you want to think about that as saying is that on the x-axis, you're less than n units away from a. So here, less than n units away. This would be a plus n, and this is a minus n. Just like this was 4, this over here was 4 plus 6, and this over here was 4 minus 6. So like that's our a minus, our n. This is our a plus n. This is our a. Does anybody have any questions on that? So it doesn't matter what symbols are in there, you'll see there's two different absolute value inequality statements in the definition of the limit. But I could also do the same exact thing for my y values. The absolute value of f of x minus w is less than p. That would say on the y-axis, I'm less than p units away from w. Does that make sense? On the y-axis. We are less than p units from w. Okay then, so with that in mind, we'll look at the definition of the limit now, here in the box. So it says that f of x exists for all x in some open interval containing a, except possibly at a. That was sort of, already present when we defined a limit initially. We say that the limit of f of x as x approaches a is equal to L. Again, we've seen that notation. And so now we know what that notation means. What that notation means is if for any number epsilon larger than 0. So just think about epsilon here as a really small number. So for any number larger than 0, epsilon, there's a corresponding number delta. So delta, again, is a really small number. Okay, so for these two small numbers, epsilon and delta, this thing happens. The absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta. So it's presented sort of like as we read it, but it really hinges on the reverse. It's really whenever this happens with the x and the a and the delta, this is going to happen with f of x and the L. But when we work these problems or you prove these limits, which we don't really get into, but when we work anything involving utilizing this definition, we do sort of reverse engineer it. We do start with the y values, and then based off the y values of that particular function we're dealing with, we sort of reverse it down to the x-axis, and then determine that right there. So in these problems, you're given an epsilon, and we're finding this delta. But what these statements mean is whenever we're delta units away from a on the x-axis, that implies that we're epsilon units away from L on the y-axis. And remember, the epsilon and the delta can be any small number, but not 0, right? So it says visually it says if depending on the function, of course, if I'm within delta units of a on the x-axis, then according to the function, that's going to force the y values to be within epsilon units of L. And then we make the distance from a little smaller, then the corresponding distance to L gets a little smaller. So it's basically like visualize as, you sort of squeeze in a window around A. The function's going to dictate what happens on the y-axis, but as we squeeze around A closer and closer, the y values are also going to get closer and closer to something else. And so what we're really paying attention to is just that window determined by these distances here. Okay, so again, epsilon units away from L on the y-axis, whenever you're delta units away from A on the x-axis. All right. So that term arbitrarily small or sufficiently close to, those are really now defined as small distances. How small? As small as we want it, as long as it's not 0, right? So these distances aren't equal to 0. Well, I think we can answer that question. In part, in question 4 here. So let's skip down to question 4. And it says, does this set the x values such that the absolute value of x minus a is larger than 0, less than delta? Does that particular region, if you will, include the point x equals to a? So we kind of know it's like this, you know, based on our diagram here, we kind of know it's like this situation. But what we want to know is, does that particular set include the a value? We know it includes all of these because all of these are within the window, right? All of these are within that window. Does it actually include that point right there? And how do we know?
Well, no, because that's 0, that's 0 away from a, right? So if it was the limit, we can't be at 0, right? So is that included?
Yeah, so you're on the right track when you say, what was your first statement? If we're at 0?
If we're at a, then you're 0 away from a.
Right, if we're identical, if we're at a, if we're at a, what is the distance we are from a? If we're right there, then we're 0 units away from a. So, does everybody agree with that? Then we need to just go back to that set and say, does that set include 0? So that statement right there, it's strictly larger than 0. It doesn't include 0. The other way to think about it is, I guess it kind of in the reverse. What happens if this does include a? So our answer is no, but if the set included a, then we would just have the absolute value of a minus a, which is equal to 0. Again, the set doesn't include 0 from that piece right there. So that little, that little notation on the end where it's larger than 0, that's the whole thing that tells us when we compute a limit, we don't care what's happening at a, because we're like super close to a but not equal to a. So when x approaches 2, we don't care what happens right at 2, because when we're talking about a limit, it doesn't include that value, whatever a is. Remember, this a it has to be specified. Right now it's really abstract, but it has to be specified that a that is in these definitions is this a right here. When we compute the limit as x approaches some number, that's that a. And so these things have to be given to make it specific. Otherwise, we just have to think of it as the value x is approaching in the sense of a limit. Same thing with L. Based off of this definition, L is just the value that y is getting closer and closer to whenever x gets closer and closer to this. So again, that's what the definition is specifying. Even though it looks a little more complicated than what's really happening, it's saying that whenever x is super close to a, remember this thing is just a really small number that's not 0. Whenever x is super close to a, does y get super close to something? And if it does, we call that L. That's the limit. Okay. So some of the homework questions we can come back to example 3, but some of the homework questions that you have to deal with in 2.7 are in relation to some of these that we have here. So we'll look at a few of these just to see how you can answer it. What we want to focus on as far as like the homework and what's going to be reflected on the exam for 2-7 is we're going to use these graphs that are given to us to find this delta, to find out how far do we have to be away from x, or how far we have to be away from a in order to make this particular thing happen on the y-axis. So the graphical stuff is what we'll have on the exam. But like question number 1 is a question similar to that on your homework. And it says, suppose you have x lies in the interval 1 to 3 with x not equal to 2. It says, find the smallest positive value of delta such that the inequality, etc., is true. So we're reading that inequality as it's larger than 0, so x cannot be 2. But we're saying that we are no more than delta units away from 2 on the x-axis. So here's the x-axis and here's 2. We're no more than delta units away. That's kind of arbitrary, but you have to, oops, wrong spot. You have to just go back up and see what they've given us is that x is in the interval from 1 to 3. So we're automatically limited by that statement. X is in the interval from 1 to 3. X is not equal to 2. So what's the smallest positive value of delta such that I'm still in that interval? It should say largest. What's the largest possible value for delta here that keeps me in this interval? What is it? 2.9? Well, so if I went 2.9 units from 2, if I go 2.9 units, I'm out here, right? .01? So that would be like, that's why it should say largest, because if I said what's the smallest value that keeps us in this interval, somebody could say it's a half, right? If I go out half this way and half this way, I'm there and there. And then somebody else could say, oh, it's a quarter. No, it's an eighth. No, it's a 32nd. No, it's a, right? So we have to talk about the largest value, not the smallest value. So then let me get rid of that. Remember what we're saying, what we're trying to answer is that we're trying to find this delta that keeps us in this window. So how many units away from 2 can I be at most? Remember, absolute value is a distance, so it takes into account your starting point, 2, and it goes from the left or from the right. It doesn't count the entire interval, right? It's either north or south, but it's not both.
So just 1?
It's just 1, right? Because from 2, I can go out 1 unit in this direction and be on this edge. So in this sense over here, delta is equal to 1. Does that make sense? Again, you've got to think about where delta is going. Even though we're saying that delta is identical to 1, that delta is going here. So I'm less than 1 unit away from 2 on the x-axis. If I were identical to 1 unit away from 2 on the x-axis, I would be here, and that's not what I'm dealing with. So in the other direction, also 1. So that's why we would say that delta, the largest delta that keeps us in that interval, not touching the endpoints, is 1. Does that make sense? Anybody have any questions on that? That's pretty much all we're doing with the graphs. So if that makes sense, then how we're using the definition of a limit will make sense. Okay. Question 2 is the exact same question, except for now it's on the y-axis. You're from 2 to 6, not equal to 4. So this, I don't know that I have enough space for it, but we go from 2 to 6 on the y-axis, and just like the a is in our our x minus a thing, so plays the role of that number with f of x. So there's 4 on the y-axis. So what's the largest possible? I don't know why they say smallest. what's the largest possible epsilon that we can choose so that we're within that window of 4? 2. Does everybody agree? Again, I'm not saying it's exactly equal to 2. I'm saying that distance is, epsilon is equal to 2. That distance is less than 2. So 2 here and 2 here. Keeps me within that window. Any questions on that? And of course, these windows are strictly determined by, one, the function that's given, right? The function affects how drastically things change, but it also is determined by how close do we want to be to something, right? Because if I want to be within 20 units of an x value, then I can look at the function and say, all right, well, if I'm 20 units in either direction from this x value, my function is going to tell me exactly how far away I am from any particular y value. So then what about if we had a situation like this where we have our, we'll just write it out, absolute value of x minus 2 is less than delta, and x is in the interval -2 to 6. No, sorry, -2 to 8. So sometimes you get a situation that does happen like this, and that's, well, I guess we'll talk about it first and then. Okay, so here's 2, this number. So what would be the largest possible delta here? So let's write that out. Largest possible delta.
4.
Would it be 4? Does everybody agree? I heard 6. 6 is true in this direction. The distance from here to here is less than 6. But the distance from here to here has to be less than 4, right? So does it make sense to choose 4? If we chose 6, it's fine to the right of 2. But if we chose 6, it's not fine for the left of 2 because it puts us out here. We don't want to go outside of that interval or that window. So when you have an asymmetric interval like this, you're going to choose the smaller of the 2 delta values. Because if you choose the larger of the delta values, on one side you're going to be out of that interval. Okay, any questions about that? So we're really reframing the notion of a limit, the idea of, hey, as I get closer and closer to this thing, what do my function values get closer and closer to? We're really defining that notion of closeness as a distance that's not exactly 0, but super, super small. So that's what allows us to get as close to something as we like without ever being there at that particular value. So does anyone have any questions? All right, so we'll take a break and then we'll start looking at graphs for these. Okay, let's see. We might go back up to we'll do this one in a minute. Well, I guess let's start with this example then. Example 3, first page. So the graph shows some function g of x And we know the limit as x approaches 2 on g of x is equal to 3. You can see that graphically as well. For each value of epsilon, find the corresponding value of delta, satisfying the condition absolute value of g of x minus 3 is less than epsilon. So again, think of that as we're less than epsilon units away from 3 on the y-axis. Whenever absolute value of x minus 2 is less than delta, we're less than delta units from 2 on the x-axis. So this starts out giving us part A is epsilon equals to 2. What I would do is when I'm given a graph, I would just keep in mind what I'm getting closer to. X is approaching 2 and y is approaching 3. So this is, like in the standard definition, that's my L and that's my A. And it says epsilon is equal to 2. I'm going to do this here. Part A, if epsilon is equal to 2, and we go back up to that inequality for epsilon, it says that, now it says specifically in part A that we're less than 2 units from 3 on the y-axis, or the g of x-axis. So we're less than, on the y-axis, we're less than 2 units from 3 on the y-axis. From 3, less than 2 units from that. Okay, so then what that gives us is a window around the value 3 on the y-axis. We're less than 2 units away, so we go up 2 units to 5, and then we're going to go down 2 units to 1. So that's our window we've marked along the y-axis, and that we know that window on the y-axis, any y is determined by the x's. So we've got to use that window and the function to determine what window are we, in on the x-axis. That gives us our delta. So we go from 5, upper value, I guess, over to the function, and then we need to go down to figure out what x value that corresponds to. So that's corresponding to an x value of 6. Same thing with the lower bound on the y-axis. Go over to the function and down to the x value here at 1. So that's why it's really important to mark your A and your L, because you always have to say, all right, from L, how many units am I from it? And then when you translate down to the x-axis, you got to know what you're referencing back. You're always referencing back that A value, the limit as x approaches whatever that number is. And then we just look at this. Well, from 2 to this bound on the x-axis, that's 1 unit. And from 2 to this bound on the x-axis is 4 units. So what's our delta? 1. Delta has to be 1. Otherwise, we're outside of that on the left-hand side. So that's our answer for part A. Delta has to be 1. Are there any questions on that? So that's all we're doing with these. That's all we're going to do for the definition of the limit. The other side of it is like proving these things with the definition, and that's really, really difficult. So in a way, I'm glad we don't have to do that. Everybody good with that? Questions? Okay. So I'm going to erase our marks here. We're going to do the exact same thing for any other value of epsilon that we're given. The limit and the A don't change. So we're going to keep those marked. part B, they give us that epsilon is equal to 1, which plugged into our definition, again, would be absolute value of g of x minus 3 is less than 1. So we're less than 1 unit away from 3 on the y-axis. So this time from 3, we're just going to go up 1 unit to 4 and down 1 unit to 2 for that window. Translate it to the function and down to the x-axis. So from 4, we're here, which is our x value of 4. From 2, we're here at 1.5. We'll mark this 4 here. So again, to determine the delta, you always start with that a value on the x-axis and go over to your boundaries. So from our a value of 2 to this boundary is 1.5. There's 0.5. And then in the other direction is 2. Delta equals 1/2. Oh yeah, a half, right? Delta is a half. So that means as long as we're so we're kind of thinking of it in reverse. If I want to be within 1 unit in either direction of 3 on the y-axis with this particular function, then that says that I have to be within 0.5 units of 2 on the x-axis for that to happen. Part A, if it says that if I want to be within 2 units of 3 on the y-axis, then I have to be within 1 unit of 2 on the x-axis. So it's sort of, you know, we'll look at a picture. It's just giving us the distance from the x and the y-axis as we traverse along. So I'm not sure let's see what A is. So A is 3 here, the absolute value of x minus A. A is 3. So that as this is in the context, this is a limit on this function as x approaches 3. And if we want to be within 2 units of 3, then that's going to say, all right, well, you have to be within a certain range of the y values. So we have to be within that blue range. Our limit's 5. But again, as we shrink that interval around the a value or the x value of 3, and we see that window that we have, the y values we have to be within are smaller and smaller, right? So from here, the y values we have to be within are 4 and 6. Now they're at 4.5 and 5.5. So I didn't actually adjust this, but let me adjust it so we can see. Now we're within 4.5 and 5.5. If I want to be even closer to 3, I have to adjust the window on the y-axis. So if we made that smaller and smaller, as the x values hone in on this thing, we can visually see that the y values close in on this thing. And that's what a limit is doing, defined in terms of distances. So that's kind of all we're doing, except for we're starting with our epsilons, getting this window here, and then saying, all right, we'll drop it down from the function. What distance does that give us from our a value? Does anyone have any questions, comments? What we're doing? And so that example we just did, again, we see why it doesn't matter. On the function, what happens as we get closer and closer to 2? It doesn't matter that the function's not defined at 2, right? But as we close in on 2 on the x-axis, the y values close in on a certain y value, and that's the limit 3. It says, part C says, for any epsilon, make a conjecture or a guess for the corresponding values of delta that satisfy this limit condition. So what they really want you to do there is to look at the relationship between our epsilons that were given and the deltas that we came up with, and see if we can find a specific relationship between epsilon and delta. So part A, we had epsilon of 2, delta was 1. Part B, we had epsilon was 1, and delta is a half. So we just want to come up with some sort of relationship between epsilon and delta. What does it appear to be, just from these two things we've computed? Yeah, smaller epsilon, smaller delta, but specifically we can come up with, at least from the limited stuff we've done here, a relationship between the two.
Epsilon equals 2 delta.
Ep-
It's twice as big as delta is.
Right. Do y'all agree epsilon equals 2 times delta? For these, though, remember it's like the thing on the distance on the y-axis happens in the definition whenever delta is somewhere. So really, you want to describe these things in terms of delta. So that's a correct relationship, but we want to see it as epsilon over 2 is our delta. So that's, that may or may not hold throughout. Part of like justifying or proving that a limit is actually what it is sort of finding this relationship first, and then going back up to the absolute values and working those out to see that it is actually satisfied. We're not doing any of that, but that's kind of the idea. Okay. Might be different. You might not always have an explicit relationship like this between the two. Like, we have this relationship here because we have linear components, but like exponential functions, logarithms, polynomials, you don't always have that direct relationship, right? Because the function doesn't always change by the same amount. Okay, any questions on part C? All right, let's see let's look at. Let's look at example 10. It's the same kind of idea. Sometimes they're written out differently. We've got the function f of x graphed, the limit as x approaches 2 on f of x is equal to 4. So here, what's our a? A is 2. A is the thing x approaches, and our limit is 4, the thing that the function approaches. So in part A, it says, for both of them, it says determine the largest value of delta satisfying the given statement, and statement in A says that our epsilon is equal to what? 1. Y'all agree? Isn't that our epsilon? Epsilon's associated with the distance on the y-axis. I mean, it's just worded slightly different. It doesn't explicitly say, hey, epsilon's equal to this, but based off the definition, it's implied epsilon is 1 in this case. So the way we interpret this statement here then in words is that we are less than 1 unit from 4 on the y-axis. So we're going to mark 4 and 2 just so we have our reference. We'll mark 4 on the y-axis and 2 on the x-axis. And epsilon is 1, so we're just going to go 1 unit above and 1 unit below 4. 1 unit above, 1 unit below. And then use the function to determine. they call it a neighborhood around 2. So if you see that word neighborhood, it's just the window that we're referring to. So this function has a negative slope, so we kind of get switched around, but that's totally fine. All we want to know is what that x value is there, and for this upper bound, what that x value is there. Okay, so based off of the limit approaching 2, or sorry, the x approaching 2 and the limit approaching 4 on this particular function, epsilon being 1, what does delta have to be? 1, does everybody agree? So then, to find that out, again, all we do is go to what x is approaching, to the right of it, count the distance in both directions, and take the smallest of either one. So that part A. So part A, delta has to be 1. And part B, similar kind of thing. What's epsilon part B?
Half.
1/2. So in part B, it says now we want to be 1/2. Let's do this in this color. We want to be half a unit away from 4. So just, do the best you can. If the graph isn't totally clear, they should be. So we're half a unit away from 4 on the y-axis. How far does that mean we're away from x? Or 2 on the x-axis. We're just going to try to get it as close as we can. So that looks like it's about 2.5. We'll just go with that. The upper bound, half a unit away from 4 above it, gives us that point on the graph. Just try to go down here. Again, we're going to reference 2 on the x-axis. That's like the biggest problem I see on the exam, is people have the correct window, but they're always counting over from the left or from the right from the wrong number. So you just want to make sure that's totally clear. From 2 to 2.5, or from 2 to 1.5, still 0.5. So in that part B, delta has to be 1/2, or 0.5. So that's really all we're doing. Does anyone have any questions? Yeah.
So for like the part B, it's a little bit less, I guess, clear. So if it was, if like an exam question has like these kind of parameters, is it like expected that we like, I don't know, like round to like the nearest half or whatnot, or is it like okay to kind of like estimate like how, like what the parameters are?
You mean what's given to us like
Yeah.
this, like all of that information? Yeah, you should know like what, in reference to the graph and what you're finding, you should know what all of that stuff is telling you. Is that what you're asking?
Yeah. I'm sorry.
Yeah, you should definitely know that. Because, like on the exam, I'll say, hey, here's a graph. A graph is going to be provided. I'm going to also say this graph is this function, and let's see if I right here. So I would say like on the exam, here's a limit given to you. The limit as x approaches 2 on the square root of I don't know. Let's say. So I would give you that limit. I would give you the graph of the square root of x plus 23. I would ask you to identify. I would ask you to identify a f of x and L based off of that, and then I would give you, just like here, I would say, all right, well. Epsilon is equal to 2. Find the largest possible delta. satisfying that limit. So again, like if your graph is provided, it hopefully makes a little bit more sense. I don't know, this isn't to scale, but if I said epsilon is equal to 2, and then find the delta that satisfies the definition of the limit, you should kind of know what we're doing. I don't know that it necessarily matters that you write down the absolute value of this minus this is less than this, but we should know that, all right, well, that means I'm 2 units from 5, and then I'm going to use my function. You know, I didn't draw this well enough, but I'm going to use my function to find the window, and then that's going to tell me what my delta is. Is that clear enough? So those are really the key things that we should be able to identify from that. Anyone have any questions about that? If that's not clear, I can. All right, so then how about you take some time and work through problem number 11. So we'll try like 10 minutes. Yeah. Yeah, sorry, I don't. Who all has this? Is that too small? Yeah, epsilons are 3 and 1. Yeah. Yeah, 3 and 1. So I just assumed that y'all printed that out. I'll try to. Was that view too small? If this is the view, is that too small for you to see? Okay, I'll just leave it right there for now.
Like for, oh, because we always want to go from the left to the right if you're yeah. Okay, so those deltas are the left and the right. The smallest of the left and the right distance from your B value, which is 2 distance, because it's neutral. So like this delta, that was the first one. I would say, all right, well, what's the distance from here to A to this window here? It's 2. 2. So that's where that delta came from. And then what I did with my epsilon was on this one. Count over again from that value to 3 to that window to that window. I would take the smaller. If they're not the same, I would take the smaller.
No. Thank you.
You're welcome. Okay. Yes. No, we're just using a graph. I mean, like, I'll show an example of how you would do it for like a linear function, but outside linear functions, it gets really, really hard. So I can actually find out. Yeah, it's like really analytical, I guess. But your textbook does a few of those. If you want to see how they do it, you figure out what the graph after you see what they do. So like, go up to that, bottom and scroll up a little more. Right there, yeah, it pops it out. Does that help? Yeah. Like that looks like 3, yeah.
Oh, wait. It's because I zoomed it in.
Oh, yeah.
Okay, got it.
Yeah.
Okay.
Yeah, that makes more sense.
Yeah.
So yeah, I guess somebody had mentioned that these notes were already filled out. I don't know why I've uploaded the blank notes. I guess it's a little too late for that, but I totally checked the file and it was totally blank, so I'm not sure what's happening with some of these files, to be honest. But yeah, so this example, seems like everyone had the correct answers. Excuse me. Epsilon is 3. We're marking that. There's our L. So we want to be 3 units from that in either direction. Here. And here. Our A is the positive 3. X is approaching 3. Mark that. Go down. X value of 1. And from the upper limit here, if you will, this y value corresponds to x value of 5. So remember, when you're doing these, to mark that a value as x approaches a, whatever x is approaching, that's your a, you're going to count to the left and to the right from that, based on your epsilon and your y values. So that's 2. That's also 2. Delta is 2. All right. So, anyone have any questions on this? All right. So. So I don't think you have any of these on your homework. I'll just make sure. And if you, I guess if you printed the notes out, you have what we're doing with this here. But I do kind of want to look at this. This won't be on the exam, just FYI. So it says use the definition of the limit to prove the following limits. 8x, the limit as x approaches 1. So from that, I'm going to say, all right, well, my a is 1 on the function 8x plus 5. F of x is 8x plus 5 is equal to 13. So can I, just from that statement, I can identify a, f of x, and L. And the definition says that the absolute value of f of x minus L absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta. So our goal, like it was with what we were doing, is we want to find that delta. But just like what we were doing with the graph, starting with the y values and then using that to determine for us what those, where those x values have to be. We're going to do the same thing with the definition when we write it out like this. So we're not going to worry about the x values situation. We're going to work with the statement involving the y values and the limits. And so we're going to simplify this. And in the most straightforward cases, you'll see like what happens is we're going to factor this 8 out. That's equal to that. The absolute value of 8 is just 8. Sorry, less than epsilon. And in the, like I said, the most straightforward cases, what happens is this. You end up with an expression after you've kind of simplified the expression involving, or the absolute value statement involving the y. You end up with something that looks almost identical to this statement right here. Right? The only difference is that we want this 8 over here with this epsilon. So from here, we would just say the absolute value of x minus 1 has to be less than epsilon over 8. And then once we have that, we know exactly what delta has to be, right? If the absolute value of x minus 1 is less than delta, and we know that that is less than epsilon over 8, there's the relationship between the delta and the epsilon right there. So what that says is that epsilon over 8 is equal to delta. And then from that, we plug this back into this thing, and then we work it sort of, I guess, forwards compared to what we were doing is working it backwards, because we're starting with the y values and determining x values, but it's always x values determine y values. But that's kind of the idea with proving limits like that. There's a couple of examples in your textbook for anyone that's interested, but I promise after probably the first example, it's going to be a bit daunting to follow. So that's why we just use the graphs. Anyone have any questions on any of this? So that'll be 2-7. We're going to review a next class period, so the review is going to be highly driven by questions you all have. I don't have set questions that I'm going to work. I can certainly say that, you know, if there's this particular concept that someone doesn't understand, we can certainly look at examples. So, you know, you don't have to come with specific examples. If it's just even a concept like from limits at infinity, we can certainly find examples to work in class, but the review is going to be highly driven by you all. I will write out the content of the first exam, meaning I'll tell you like what kind of questions, how many questions for each topic are going to be there, and then maybe you can use that to sort of, you know, guide your study and questions on Tuesday.
So like if we bring questions from the homework and it's not given the exam, we just tell us, don't worry about it.
Yeah.
As far as the exam goes.
Yeah, maybe. Maybe, I don't know, that's a tough one. Because then it's like, oh, that homework question's not important, don't do it. That, you know, like I don't want that to come across, but I don't know, it's kind of a gray area. Okay, so the content of the exam, every exam will have short answer, multiple choice, true, false type questions. So expect that on every exam. And if we don't finish this, we should be able to get this through in 15 minutes, but if we don't, we'll pick back up on Tuesday. So there will be a multiple choice. True or false. Short answer. And typically those questions aren't worth a whole lot of points, but they are more conceptual than they are actual problems to work out. So like an example would be, like if I said, given the limit as x approaches a from the left on a function f of x is equal to 2, the limit as x approaches a from the right on the same function is equal to 5. What can be said about the limit as x approaches a?
Doesn't exist.
Yeah. So, you know, more conceptual type questions that apply broadly, not specifically to one concept maybe. So something like that. And, you know, short answer, you could just say does not exist, because you know that in order for a two-sided limit to exist, the one-sided limits have to be equal. So that's kind of the idea with multiple choice true false or short answer. It's really hard to say know these particular things, because it's more of a it's conceptual. Have you done your homework, and have you like realized in certain situations this is what happens, you know? So they're kind of hard to be specific without giving away the question. So, you know, stuff like that. I hope that's good enough. I'll just circle the question numbers. So you'll have one question where you're given a position function, s of t. You want to find the average velocity. The average velocity. On or, yeah, we'll say on specific intervals. Then make a guess about the instantaneous velocity. So this was what we did in 2.1, the very first section. The thing to remember here is when you compute the average velocities. Remember, the average velocities were what? How do we compute average velocities? Yeah. So the average velocity on some specific time interval, it would be like, you know, I don't know, whatever. I give you time 1 and time 2 like this. From 1 to 1.5. Or from 10 to 11. But the average velocity was just the slope of the line connecting those two points. So it was the position at T2 minus the position at T1. There's the change in your Y values over the change in the T values. So then the instantaneous velocity comes about by doing what? Well, yeah, the limit, right? In this kind of situation where we're just given intervals, what does the limit look like? What happens to our time intervals? You're right, they're shrinking. So it's like find the average velocity on the interval from 10 to 11. Then find the average velocity from 10 to 10.5. Then from 10 to 10.1. Then from 10 to 0.001, right? So just almost identical to what we did in 2.1. The average velocities are not your instantaneous velocities, nor if I said, what's the average velocity, or sorry, what's the instantaneous velocity at a particular time? You're not going to look at the position function evaluated at that time. So a lot of times what happens is if I ask what, based on your slopes here, what is the instantaneous velocity that's t equal to 10 or whatever it is, a lot of times I have people, because this function is actually given to you. So whatever, let's just say it's negative 3t squared plus 4. A lot of times people just want to take that t value to answer the question about the instantaneous velocity and plug that into the position function. So just, I don't know, if that seems trivial, then awesome, but don't do this. S of 10 is not the instantaneous velocity, that's your position at 10 seconds, right? To find the instantaneous velocity, you have to compute these averages, whatever number you get here, over smaller and smaller intervals, and you have to look at what that number approaches. Does that number seem to get closer and closer to a particular number as these time intervals get smaller and smaller? Okay. So one question like that. One question where you're given a graph. Evaluate function values. Limit. And discontinuities. And for the discontinuities, make sure that you're able to justify with the checklist. In other words, saying, well, the function's discontinuous at 5 because there's a hole, that's not going to quite cut it. We had 3 items on the checklist for continuity. So I know this is very generic, but we have 14 questions where you have to evaluate a limit. So those are, like for example, they're going to be given. For example, what's the limit as x approaches infinity on 3x to the 4th minus x plus 2 over 3x cubed minus x plus 3. Something like that. Can't really be too specific with these because section or chapter 1 or chapter 2 was just really about limits. So you should be familiar with those.
So like if we take this one in particular, would you want like an answer like limit is at infinity or limit does not exist or both? Or like, how would you want that explained?
Yeah. So if your limits are, if you have an infinite limit, if the limit comes out to be infinity, as it should here, then you would explicitly write that. So it'll say state the limit does not exist, or write infinity or negative infinity when appropriate. But it's kind of this a point of confusion, because when you have a limit that comes out to be infinity, it's true that it doesn't exist. It just tells you, it just gives you a little more information about what we're actually doing. So anytime you have a limit that evaluates to infinity or negative infinity, write that out. Don't just say it doesn't exist. Because the point is with limits, there's always context to them, right? It's not just this mechanical computation that has no meaning. It says, on this function, the end behavior is infinite. So like, whatever this function looks like, whenever I'm way out here, I know the function's way up here because of that limit is infinity. If I just said that limit doesn't exist, it doesn't give me any information about the function as it should give me information. So yeah, the instructions will be like, write infinity or negative infinity when appropriate. Okay, so the limits we looked at, there were many limits. We looked at limits infinity. And this was also end behavior. So again, if the question says state the end behavior of this function, you should know to compute the limit at infinity and the limit at negative infinity. We had limits at infinity and infinite limits. This, by the way, was section 2.5, limits at infinity. Section 2.5, infinite limits, section 2.4. Infinite limits. So then, you gotta be well aware of the concepts. We just saw an infinite limit that was infinity, right? But infinite limits mean that usually what they meant was the limit as x approaches a, as we approach some finite number, the limit turned out to be infinite. But it could certainly be the case in like with like polynomials, we can have infinite limits at infinity. So you can have both concepts kind of together. The difference is anytime you compute a limit as x approaches infinity, that will always determine the end behavior, or if the function has horizontal asymptotes. If you approach a finite number and the limit is infinity, that will always correspond to vertical asymptotes. So these things were vertical asymptote at that x value we approach. Okay. So again, these concepts you should know. Like you should be, not only should you be able to compute a limit, you should know like what it means. Like so if I said here's a function, identify the vertical asymptote, and then use limits to state the behavior around the vertical asymptote, you had a couple of homework problems like that. You should know exactly what to do. Like it's fine to like algebraically reference, oh hey, this function has a vertical asymptote at 7, but then if I said use limits to show the behavior, then you need to actually say, all right, well, what's the limit as x approaches 7 from the right on whatever function I'm working with, and what's the limit as x approaches 7 from the left on this function. It shouldn't be an algebraic evaluation. You should be able to do this and say, oh, whether it's up here or down here from that direction, or whether it's up here or down here from the other direction, by justifying with limits. Is that clear? Does that make sense? And so, I mean, we can certainly look at examples and expand on any of these things on Tuesday. We also had certain limits we could simplify where we could factor. There was radicals that involved conjugates. Complex fractions which involve the lowest common denominator. All of these are examples that we've worked. Trigonometric limits. So really, any limit we've worked in class could be there. So 14 questions for limits there. There is one question where you're given a rational function. Remember, a rational function is a polynomial over a polynomial. So given the rational functions, you want to identify the discontinuities. Like the whole or vertical asymptote, that kind of thing. identify the discontinuities, state the vertical asymptote or vertical asymptotes. Horizontal asymptote. And the whole, and with all three of these, you should be able to justify or show your work and how you know where the whole, the horizontal, and the vertical asymptotes are by using limits. Okay, there's actually a couple of more items that we'll add to on Thursday. I don't know that we have enough time to write them down. So definitely, like I said, one from 2.7 where you're given a graph is also going to be on the exam as well. So see you all on Tuesday.